As I mentioned briefly at the end of part one of this lecture, it's fortunately possible to calculate the expected deltaH of reaction for many reactions by using experimental data obtained over decades for thousands of other reactions. Now, before illustrating these calculation methods, we need to note two things about deltaH and Q. First of all, they change signs when the reaction they represent is written in reverse. And secondly, they're both extensive properties of reactions, meaning their magnitudes depend on the actual masses of reactants and products. Let's look at a couple of examples of what I mean. The reaction of diborane gas with oxygen is very exothermic. So you don't have to have much appreciation for this reaction specifically. It's just a combustion reaction of a toxic compound. The point I want to make here is that it's very exothermic. So you notice the deltaH for this reaction. And remember, this is for the reaction written from left to right, is minus 2035 kilojoules. That means the reverse reaction would require an input of heat energy. In other words, it would be endothermic. And the deltaH for the reverse reaction would be the same number, only positive. So if we wrote this reaction in reverse and said, now the reactants are what the products were up here, we write it in reverse, that means this would now be energetically uphill, if you want to think of it that way. You'd have to put heat energy in from the surroundings into the system to get it to go. So the deltaH is the same number but opposite sign of the deltaH for the reaction written up here. So again, the deltaH changes sign if you write the reaction in reverse. Let's look at another example. The decomposition of ammonia into nitrogen and hydrogen is actually an endothermic process. deltaH for this reaction, written left to right, is positive 92 kilojoules. Well, what would be the deltaH for the reverse reaction that's also multiplied through by a factor of 2? So what I've done here is I've reversed the reaction, but I've also multiplied everything through by 2. So we have 2 nitrogen molecules, 6 hydrogen molecules, 4 molecules of ammonia. The deltaH here is minus 184 kilojoules. Why? Well, we reverse the reaction, so we change the sign, but we also have to multiply deltaH through by 2 because we multiplied everything in the reaction through by 2. Because remember, deltaH and Q are extensive properties. So the more material that you're dealing with, the more heat flow that you're dealing with. So you would change the sign of deltaH and multiply its value by 2. The new deltaH would be 2 times minus 92 kilojoules, or minus 184 kilojoules. Well, you might ask, well, this is nice, but how does it help us calculate the expected deltaH values for reactions which we are not able to or don't want to measure experimentally in the laboratory? Well, let's find out. Let's suppose you were given the following 3 reactions and their deltaH values. In other words, this is supposed to be experimentally determined values of deltaH. The first would be for the reaction of hydrogen and oxygen to form water, and the deltaH for this is minus 285.8. It's an exothermic reaction. Let's suppose the reaction of N2O5 with water to give 2 molecules of nitric acid is exothermic by minus 76.6 kilojoules, and that the reaction of nitrogen and oxygen and hydrogen to give nitric acid is exothermic by minus 348.2 kilojoules. So what we're asking here is, knowing these 3 reactions, the way they're written and the deltaH values for each, calculate the deltaH for the following reaction. Nitrogen plus oxygen going to N2O5. So we're saying, what would you estimate that deltaH to be based on these values and equations that you're given up here? Well, simply what you need to do here is find a way to rearrange and then add together equations 1, 2, and 3 to give the desired reaction. The deltaH values of the rearranged equations will then add up to give the deltaH of what we call the target reaction, meaning the reaction that we're after here. So let's see how we do that. I'm going to start by taking equation 3 and multiplying through by 2. So when I do that, I multiply everything here through by 2, which means I have to multiply the deltaH by 2. I don't change the sign of deltaH because I didn't reverse this reaction. I just multiplied through by 2. So we have minus 696.4 kilojoules as a result. Now you might ask, okay, this looks random. Why did you choose to do this? Well, my choice is based on the fact that in the target reaction, N2 gas is on the left, so I want to leave it on the left. And there's a 2 in front of the N2 gas, so that's why I multiplied this equation through by 2, so I get 2 nitrogen molecules. And at least we get something that starts to look like this target reaction. I'm now going to take equation 2 and reverse it and multiply through by 2. Well, why would I reverse equation 2? Well, the reason I'd reverse it is because in the target, N2O5 is to the right of the arrow. It's a product. So I'm going to reverse this reaction, so N2O5 is a product. I'm then going to multiply through by 2 because I want 2 moles of N2O5. Well, here the deltaH contribution from this step is 2 times minus a minus 76.6. In other words, I changed the sign of deltaH and multiply through by 2. So now we have positive 153.2 kilojoules contributing from this step. And then finally, I'm going to reverse equation 1 and multiply through by 2. Well, when I do that, I get this. Again, why would I do that? Well, I'm not sure I could give you a good reason right offhand, because when you look at this equation, it doesn't seem to help us to do that. In fact, the oxygen here is a product and it's a reactant here. So you might ask, why are you doing this? You'll see in a second. It has to do with getting the proper species to cancel out when we add these equations together to get this target. The deltaH here would be 2 times minus a minus 285 since we reversed the reaction, or 571.6 kilojoules. So now I think I'm ready to add these up. And what I'm going to do is cancel out things that are the same on both sides of arrows. So there's 2 water molecules on the left of an arrow here and 2 on the right of an arrow here, so they cancel. The hydrogen molecules cancel, 2 of each here on the right of the arrow, 2 of each here on the left of the arrow. And the nitric acid molecules cancel, 4 here on the left of this arrow versus 4 here on the right of this arrow. If I take what's left and add it up, I wouldn't quite be there. So I'm going to cancel this 1 oxygen molecule on the right of this arrow and 1 oxygen molecule from the left of this arrow, leaving 5. Now note, if I take what's left, 2 nitrogens plus 5 oxygens on the left of the arrows and 2 N2O5 on the right of the arrows, I get my target reaction, which means that I now simply have to add up the deltaH's right here to get a net deltaH, net overall deltaH. And when I add those up, I get 28.4 kilojoules for the estimated overall deltaH for this reaction using this supplied, hopefully, experimental data. So this reaction of nitrogen and oxygen to form N2O5 is estimated to be slightly endothermic. You might ask, why were we constantly multiplying by 2? Is that a thing for all the examples? No, it just turned out that in this particular example, we multiplied by 2 a lot to reach our target reaction. The other thing you might ask is this the same sort of process for every example I would see? And the answer is yes, it's the same sort of process, but each one is unique. So you just have to solve the puzzle. How do I get these 3 reactions rearranged so that when they add up, they give me the target reaction? And again, you'll note on this last one I did that just because I knew I was going to need to cancel some things out, and having the reaction written this way was the best way to do it. Well, in case you're still awake at this point, the example problem we just did illustrates something called Hess's law. And that is, if a reaction can be written as the sum of a series of steps, so we wrote this reaction as a sum of a series of steps, then the delta H for the overall reaction, meaning our target reaction here, is simply the sum of the delta H values for the individual steps. But you'll notice I just didn't add these 3 delta H values up. I added the delta H values up of the rearranged equations. We can also calculate or estimate the delta H for a reaction using what's called standard enthalpy of formation values, delta H sub F with a little superscript 0. If the delta H value is measured for a reaction where a compound is formed from its elements in their standard states, we call the measured delta H value for the reaction the standard enthalpy of formation, and it's symbolized by delta H sub F superscript 0. You might also see these values referred to as standard heats of formation. You would justifiably say at this point, what are you talking about? Well, let's just do an example and show you. Let's consider the formation of carbon dioxide gas from its constituent elements carbon and oxygen. If I wrote an equation for that, I write carbon solid, because that's the standard state of carbon at 1 atmosphere of pressure and 298 K, and O2 gas, because gas is the standard state of oxygen under 1 atmosphere of pressure and 298 K, that the formation of CO2 under these conditions would give a delta H value of minus 393.5 kilojoules per mole. And because it's a delta H that's determined for the formation of CO2 from its constituent elements in their standard states, we call it something special. We call it the standard enthalpy of formation. So this subscript F here just reminds us that this delta H value refers to an enthalpy of formation, and the little superscript 0 reminds us that the delta H value is for the formation reaction under standard conditions. Each gas at 1 atmosphere of pressure, if there's solutions involved, they're 1 molar. Solids and liquids are in their pure forms, and elements are in their standard states at 298 K. General chemistry textbooks typically provide tables. They're fairly long tables of standard enthalpy of formation values for many different compounds. What I've done here is I've copied just a little slice of a table that's available in D2L, and that's also in Appendix C of your textbook. And you'll notice here that there's a column for standard enthalpy of formation values in kilojoules per mole for all these various compounds in various physical states. So in the example above, I got this data for CO2 from the table, minus 393.5, and we know it's for this reaction because it's for the formation of CO2 from the elements carbon and oxygen under standard conditions. These two columns that you see in tables we'll deal with in future lectures. Before we can show an example of using standard enthalpy of formation values to calculate the deltaH of a reaction, we first probably need to give you a little heads up about the values that you'll use from these tables. Let's look at that on the next slide. For elements in their standard states, the heats of formation are defined as 0. So for example, if you looked up the heat of formation, or the standard enthalpy of formation, for calcium in its solid state, it would be 0, because this is the state of the element calcium under standard conditions. It comes as a solid. For elements that are not in their standard states, the heat of formation values are not 0. So for example, if you looked up the heat of formation for the element calcium in the gas form, it's not equal to 0. In fact, it's equal to 179.3 kilojoules per mole. Well, it's an element, calcium, so why isn't it 0? It's because it's in a state that's not its standard state under standard conditions. So under standard conditions, calcium is a solid, it's not a gas. If you did form calcium in the gas form, it would take some energy to do that, so it's going to have a heat of formation value. The standard state for aqueous solutions is for aqueous solutions at 1 molar concentration. You'll find that tables of standard enthalpy of formation values will list a value, for example, of minus 167.2 kilojoules per mole for an aqueous solution of chloride. This would be for a 1 molar solution. For a 1 molar solution of sodium ion, you get a value, if you get the right table, of minus 240.1 kilojoules per mole. And not surprisingly, the value for a 1 molar solution of sodium chloride would be pretty close to the sum of those two numbers. Now we can use deltaH sub F values from tables of available data to calculate deltaH values, in fact, the standard deltaH values, by using the following formula. The overall standard deltaH change for a reaction is the sum of all of the heats of formation of the products minus all of the heats of formation of the reactants. And you have to keep in mind that you need to track the number of moles of products that you have and the number of moles of reactants that you have in the balanced equation. So let's look at an example. The first step in the manufacture of nitric acid is the formation of NO gas and water from the combustion of ammonia. And the balanced equation for this is, of course, ammonia plus oxygen. That's a combustion reaction forming NO gas and water vapor. The balanced equation looks like this. And what we want to do here is use standard enthalpies of formation values listed in the supplied table here to calculate the overall standard entropy change, or excuse me, standard enthalpy change for this reaction. So what I did here was I supplied a table, and these values come either from the table in your textbook, or if they weren't available, from tables from other textbooks. And remember, the overall standard enthalpy change you can get with this formula here, and let's see how this would pan out. The overall deltaH is equal to the sum of the deltaH values of all the products multiplied by how many moles there are of each. So the products are NO and water. So I'm going to take 4 moles of NO, because that's how many moles I had in the balanced equation, and multiply from this table that for NO gas, I forgot to put the state symbol there. And I guess I slipped up over here too. I might have done this because I ran out of room. I'm going to multiply by 90.37 kilojoules per mole of NO. And of course, moles of NO cancel. Then I'm going to add 6 moles of water vapor times minus 241.82 kilojoules per mole of water. I think I made sure that the state sign was given here for water vapor because you want to make sure it's water in the gas form, not water in the liquid form. Two different values because water's in the gas form in this equation. And so moles of water cancel. And then I'm going to subtract the sum of all the heats of formation of the reactants. 4 moles of ammonia times minus 46.19 kilojoules per mole of ammonia from this table. And of course, the value for the enthalpy of formation of oxygen is 0 because this is oxygen gas in its standard state. We have to be careful about how we go about doing this calculation, not because it's difficult, but because if you're distracted while you're doing it, you're going to mess up some of the additions and the signs. So what I did was I kept the products in this bracket here, and the result from NO is 361.48, and I'm going to add the negative 1450.92 that I get from oxygen, close the bracket, and I'm going to subtract the sum of minus 184.76 from the ammonia plus this 0. What this then looks like is the sum in this first bracket is minus 1089.44. The sum in this bracket is minus 184.76. And remember, we're subtracting what's in the second bracket. So in effect, minus times minus is a plus. So we end up with minus 904.7 kilojoules for the overall delta H under standard conditions for this reaction. It's an exothermic reaction. Again, I want to emphasize that when you read delta H of formation values from tabulated data, make sure you're using data for the phase of each substance shown in the reaction. So for example, as I mentioned, this reaction had H2O gas as one product. If you mistakenly use the delta H value for H2O liquid from the table, which is minus 285.83, you would not arrive at the correct delta H for this reaction as written. This ends our review of General Chemistry 1.